Hello everyone, welcome to 2021 P4 workshop. I'm Guru Parulkar. I serve as the Executive Director of Open Networking Foundation and Executive Director of Stanford Platform Lab at Stanford University. I'm going to help coordinate this recorded session about programmability in NICs for congestion control and transport protocols. I'm delighted to welcome two distinguished speakers from Google, Nandita Dukkipati and Konstantin Weitz. Let me do quick introductions of Nandita and Konstantin. Nandita is the principal engineer leading congestion control and host telemetry systems at Google. Her team is responsible for delivering excellent end-to-end network performance for applications. She has published award-winning papers in premier networking conferences with numerous contributions to congestion control, low latency networking, network isolation, and bandwidth management. She received her PhD from Stanford University in 2008. Konstantin, he is Google's go-to person for everything P4, including switch and NIC applications. Before joining Google, Konstantin received his PhD from the University of Washington, where he worked on formal network verification. Nandita and Konstantin, welcome to the P4 workshop, and please take it away. Look forward to your talk.
Thank you very much, Guru, for the kind introductions. So, hi everyone. Today, I'm joined by my co-presenter Konstantin, and Konstantin and I will talk about programmability in NICs for congestion control and transport. So we started out this talk asking ourselves three key questions. What transport and congestion control capabilities make sense in NICs? Which of these transport capabilities actually require programmability versus which of them can actually be baked into hardware? And can the transport functionality be expressed using P4? So in the rest of the talk, we are actually going to touch upon a sliver of these questions. This talk is structured as follows. First, I'm going to start out with some context on why do we actually care about congestion control at Google and capabilities for transport in NICs, and why does it actually matter? Then we're going to deep dive a little bit into Swift congestion control, taking it as a running example through the talk. And NIC time as a service as one of the key capabilities in NICs that we care about. We intended to talk about traffic shaping and scheduling in NICs, but unfortunately we won't have time in this particular presentation. So we will then jump on to a deep dive example of expressing Swift congestion control aspects with P4. So let's start with why congestion control at Google matters and why do we care about it. Very broadly speaking, bandwidth management in Google is along these four key dimensions. The first one right on the top is per flow congestion control, which is typically done using Swift and BBR congestion algorithms. Per flow congestion control has typically traditionally resided in TCP-based stacks. However, more recently with RDMA and OS bypass transports, there is congestion control in non-TCP-based stacks as well. For some aggregates, particularly over those going over the wide area network systems, we also have large-scale centralized entities such as the bandwidth enforcer that measure bandwidth usage and congestion created by different jobs accessing the wide area networks. And they compute bandwidth allocations for different jobs. So systems like bandwidth enforcers or B4's traffic engineering are operating over aggregates of flows as opposed to fine-grained flows like what per flow congestion control does. Then we also rely on QoS or quality of service, queues, scheduling at the switches for even coarser-grained bandwidth sharing. The final fallback are static limits. These are static limits for bandwidth configurations based on CPU cores or the storage purchased. So the point that I want to get across in this slide is that data center networks make huge amounts of investments for bandwidth, and therefore constructs for effective use of this bandwidth are important. And today, these constructs lie largely in the transport capabilities in the host networking stacks and the NICs. So let's take a quick look at what the structure of transport and congestion control looks like in today's host stacks, all right? This diagram very broadly shows the overview of the transport in host networking stacks. This diagram is inspired by Pony Express, which is a networking stack providing custom reliable transport, but similar concepts hold for other networking stacks as well, both software and I hope in future going forward, even in NICs in hardware. Pony Express provides command and completion queue API, which is shown out here, where applications submit commands to Pony Express, which are also known as ops, and they receive completions. Ops map on to network flows, where different packet level constructs actually manage the various aspects of flows. What we will be focusing in the rest of the talk is actually mostly restricted to this packet level transport layer, of which I've divided it into roughly 6 building blocks. Congestion control, which modulates the rates at which a flow is going to space out traffic. Reliability engine, which determines which packets are lost and in what order do packets or retransmissions need to be made in order to for 100% recovery. Scheduler and traffic shaper that actually comes in a few different contexts in terms of scheduling not just packets, but also flows and even higher level operations. Flow management or connection management, definitely, and as well as ordering in terms of both packets, operations, and flow and admission control. The last two of these is actually a cusp between an intersection between the transport layers and the op layers. Now, for each of these building blocks, I believe that there are aspects that some aspects that we care about programmability and some aspects that need to be baked into the hardware. What we're going to do in the rest of the talk is actually just going to take one of these blocks, congestion control, and see what aspects of congestion control actually need to be programmable versus those aspects that are okay to be baked into the hardware. So we're briefly going to talk about Swift congestion control, which we're going to take as a running example through the rest of the talk. But we hope that some of these takeaways and learnings actually are applicable to congestion control in general. So what is Swift? Swift is a delay-based congestion control for data centers that achieves high utilization, high bandwidth, low latency, near zero packet loss. It's implemented completely in end hosts, supporting diverse range of workloads, even under pretty stressful traffic patterns like large-scale incasts across latency-sensitive applications, byte-intensive applications, and IOP-intensive traffic, working in heterogeneous data centers. At scale, Swift achieves in our data centers short tail latencies in the order of 50 microseconds for short flows, while maintaining near 100% utilizations at line rate. The two main drivers that actually motivated us to invest in Swift and come up with Swift. The first is performance, tail performance of short flows motivated by the needs for resource disaggregation. And second is CPU efficiency. Even as we go to 200 gigabits per second, it's important for us to be able to operate transports and congestion control efficiently CPU-wise. So the core aspect of Swift design is it's based on delay decomposition. It measures end-to-end delay using a combination of hardware and software timestamps, and it decomposes this end-to-end delay into various different components as shown in this figure, such as the delay experienced in the local NIC TX queues, the delays experienced in the fabric, as well as in the remote NIC receiver queues from the perspective of a Swift sender, of course. Similarly, the delays experienced in the reverse fabric side and for the returning acknowledgement path, the delay that it experiences at the local RX side. Using such a decomposition of different delays, Swift is able to decide explicitly which of these delays that it should respond to, right, and how it should respond to. For example, there are situations where we only want to respond to the fabric delay and not so much as to the end host delay. And there are other situations where we want to craft different responses to the end host delay, wherein we want to respond to the RX delay in the queues, but not so much as to the processing delay at the host networking stacks, because this processing delay is not going to go away just because congestion control is going to respond to it. In order for Swift to get the complete flexibility after breaking down, decomposing this delay into different components, it modulates or maintains two separate congestion windows. One congestion window is meant for to handle the fabric congestion, wherein it only considers the fabric delay into account. And the second congestion window is meant to address the endpoint congestion, where it takes in some combination of the congestion experienced at the local host and the congestion experienced at the remote host. In general, the effective congestion window is the minimum of the fabric and the end host congestions. So what you've seen in the last slide is a general conceptual representation of Swift's end-to-end delay. What is shown out here is, in practice, the exact timestamps that we care about that Swift uses. There are 4 timestamps that Swift very heavily relies on, which are shown as T1, T2, T3, and T4 in the slide. And using a combination of these timestamps, Swift is actually able to compute the entire round trip delay, which is T4 minus T1 out here, or the fabric only components, which it can do so by subtracting out the delays experienced at the end host. And in future, if these times are even synchronized with synchronized NIC clocks, we can even compute the forward only round trip, forward only delay as T2 minus T1, or the reverse only delay. So just access to these timestamps gives a powerful set of constructs to build congestion control on. So once we have access to these timestamps, Swift is pretty simple. It's actually a very simple additive increase, multiplicative decrease algorithm, the well-known AIMD mechanism that is used in many congestion controls. And it uses a simple AIMD based on the target delay. For example, if the delay is lower than the set target, where the set target delay is a key variable in Swift. It's a key tuning knob in Swift because it determines the end-to-end delay that we are willing to tolerate between any 2 hosts in the data center. So if the delay is lower than the set target, Swift increases the congestion window additively. Whereas if the delay is above, the measured RTT is above the target, it decreases the congestion window multiplicatively. And we've already talked about the use of the hardware and software timestamps. It uses a combination of them to be able to decompose the delays at different segments in the fabric and the hosts. And the third point out here on the slide is that Swift seamlessly transitions between congestion window and rate. Most of the time it operates in the congestion window mode. However, under extremely large scale incasts, say, think about tens of thousands of hosts communicating to a single server, when the operating point is actually can get to lower than 1 packet per round trip time, Swift resorts to the rate mode, wherein it enforces the rate using a scheduler, such as the timing wheel, and to pace out packets, such that each of the packets from these tens of thousands of flows are paced out smoothly in order to alleviate congestion at this link incoming to a server. And the final slide on Swift design is essentially these three other capabilities, where in the target delay that we just spoke about is not set to be a constant in our data centers. It is scaled adaptively based on both topology and congestion at the flows. So it's scaled on topology quite easily because we know the exact number of hops between a sender and receiver in the data center. So scaling the target based on topology allows Swift senders to be able to achieve RTT level fairness regardless of the path lengths that they are traversing. Flow-based scaling essentially allows Swift to put on the brakes hard or easier depending on the level of congestion that is happening. It takes into account contention due to on the buffer when there are a very large number of flows. Finally, because Swift actually works really well in terms of maintaining the end-to-end delay to the set target, we've found very little need to invest in very rich loss recovery schemes. So we have basic loss recovery schemes based on selective acknowledgement and RTO-based schemes. So taken all together, knowing what we know on Swift and congestion control, so we think that we can think of the programmable and the non-programmable aspects of congestion control in the following way. For instance, timestamps or any other congestion control can be baked into hardware. These are things that a NIC should do really, really well for all of the data paths, whether it's for RDMA or the LAN paths. Similarly, enforcement of congestion window or the rates, right, which we do so in today's timing wheel, again, should be done really fast, really well in hardware and can be baked into it, at least from Swift perspective. There are other reasons why we might need programmability into schedulers and shaping traffic shapers. And the key programmable plane really needs to be the part that that plays about with the RTT measurements from the timestamps. Decisions such as, do we take instantaneous RTT into account, or should it be an exponentially weighted moving average, or should it be something else, right? And those are the parts that we need programmability for. Similarly, for the rate computation engine, how exactly should the congestion window be computed based on these timestamps? How should the fabric window be computed versus the endpoint congestion window? And how should the rate be computed? When should we switch over from congestion window to rate? These are the kind of decisions that we think can benefit from a programmable plane. So next, I'm going to hand it over to my co-presenter, Konstantin, who's going to take the Swift framework and dive a bit deeper down to show us what it takes to express some of these constructs in Swift in P4. Konstantin, on to you.
Yeah. Thank you, Nandita, for the background on congestion control in Swift. If you want to go to the next slide. So, Nandita just talked about the basic building blocks of Swift, right? And I want to bring that down into a more familiar thing to some of the P4 audience in this talk, right? So really, Nandita talked about this measurement and rate computation engine. And that's a block in the NIC that needs to be programmable. And the input to that block are the acknowledgements that we get from Swift. So right, we send a packet over the wire, we get back an acknowledgement. And the acknowledgement contains all these timestamps that Nandita has talked about. It also contains the connection ID that allows us to, know what connection that packet is part of. Right, so we have this packet, it goes into our computation or into our engine. And then we also get the connection state for that packet. And the most important part of the connection state is the congestion window. this basically tells us how fast we can send packets out. Formally, this is defined as the maximum number of unacknowledged packets in the network, right? If that's higher, we can send out more packets. If it's lower, we need to wait for more acknowledgements before we can send packets out. Okay, and so again, what we do is we take these packets, we put them into our engine together with the connection state, and then we produce another congestion state with the updated congestion window. All right, if you go to the next slide. So is P4 right for this, right? If you look at that picture, it's kind of maybe a bit of a wash. So let me think why I think it's right for it. I think fundamentally, right, the way I think about P4, you know, there's many distractions around packets and tables and so on. But fundamentally, you take fixed size inputs, like a packet in this case, and the connection state, and then you create a fixed size output. In this case, another connection state. And it's important that you do this in a fixed amount of computation, so you don't have loops or recursion, so it can be implemented efficiently in hardware. And all of these are true for congestion control. But of course, there's also challenges, right? Like in P4 PSA, we couldn't really express this, right? We just don't have the right standard metadata, and you know, you have like an ingress and egress pipeline that doesn't quite fit, right? So we're actually very excited about the developments in PNA, and we think we can probably, you know, I don't think it's quite there yet to express this, but we can probably guide the community in the right way. And then I think another challenge is, right, we have Barefoot has been very good at providing hardware for switches to compile P4 programs to, right? These are kind of different programs. We need more state, more registers for the connection tracking. We also need more ALUs to do all this computation, right? Probably need fewer TCAMs. So I think there's a different kind of hardware that we need. All right, do you want to go to the next slide? Thanks. All right, now let's dive into the code. You know, what does this engine actually look like in P4? So as Nandita pointed out, right, the first thing we want to do is we want to compute the round trip delay that the packet actually took. And so we have these timestamps. T1 is when the packet was sent. T2 is when it was received, right? If we subtract those, we get the time it took to send. And then if we do T4 minus T3 and add that to it, we get the entire fabric round trip time. And so we can obviously express this fairly easily in P4. Next slide. Okay, so once we have the fabric round trip time, we compare that to the target. And then what we do is we adjust our congestion window proportionally. So very concretely, say it took 60 microseconds for the packet to go to the other NIC and come back, right? And our target is 40 microseconds. Then what we would do is we would adjust our congestion window proportionally. So right now, if we're sending out 3 packets per round trip time, we would now only send out 2. So we're slowing the rate at which we're sending. And you know, you can write this math down in P4 as well, right? There's a little bit of a subtlety. It's not quite proportional, but it's easy to express. Okay, can you go to the next slide? All right, and then lastly, we also have a case where we increase the congestion window, right? We're not sending as many packets as we could. And we notice that when the round trip time is lower than our target. And in that case, what we're doing that every round trip time, we want to increment our congestion window by 1. And that's actually implemented in a funny way, because every time we get an acknowledgement, we increment the congestion window by a fraction of 1, so that once we've received all the acknowledgements in an RTT, we increment by 1. And again, we can implement this you know, in a fairly straightforward way in P4. Next slide. All right, great. So I hope that this gives a bit of context of how we would express this in P4. Now I want to highlight that this is, you know, a snapshot in time, right? This is what we're doing right this second. But, you know, we have very definite plans, like in the immediate future, change these things, right? So we can't really just hard code these things in the hardware. So for example, in addition to the timestamps that we have right now, we also want to, we're thinking about synchronizing the clocks on the NICs very precisely so that you can compute the one-way delay. So you can compute how long it took for a packet just to be sent to the other host. You don't just need to compute a round-trip delay. That's on the hardware side, but on the programmability, there's also lots of trade-offs that we can make, right? And lots of options that we're exploring, right? So you can have an instantaneous round-trip time, or you can have a windowed round-trip time. You can infer the congestion at the host, but you can also do it in the fabric or at the sender or the receiver, right? There's many options, and similar to the congestion window adaptions, right? You can do based on RTT, or once we have the one-way delay, you can also use that. Right, I hope that gave you a bit of a background how we could model this in P4. I'm very excited about this, and let me hand it back to Nandita.
Thank you, Konstantin. So let's just briefly look at a few takeaways from this slide. So in this work, while we have shown you a sliver of the work on how congestion control and its capabilities that we care about, it can be expressed in P4, but I think there is a large amount of actually just very interesting future work that remains to be done. Specifically, we've spoken a little bit about, mentioned just the other blocks such as reliability, scheduler, flow management, admission control, ordering. I think one of the things that we have ahead of us is which of these other blocks actually require programmability, or what aspects of these blocks require programmability versus those that can be baked into hardware. And then the question is, can we express the programmable aspects in P4 or P4 prime or P4++, right? And after that, I mean, there is an open problem of building hardware to run P4 expressed transports. So we think that this is a very exciting and open set of problems that we in the community can solve. So Konstantin and I want to thank many contributors that led us to this talk, Yulin Lee for his direct contributions to P4, Swift on P4, and several others at Google, including the congestion control group at Google that shaped our thinking on this talk. Thank you.
Hi, Nandita and Konstantin. Very good talk, very insightful and stimulating talk. So thank you again. So I have a couple of questions. So let me start with a clarifying question first, and pardon me if this is well known in the community and I'm the only one who doesn't know. But tell me, what is the status of Swift and BBR in the Google data center? Have they become the default protocols or algorithms in Google data centers, or they are still in the exploratory state? So what is that status?
Sure, great question. No, they are, while congestion control is perpetually in exploratory state, both inside and outside of Google, but the state of Swift and BBR is within Google is they are definitely more than just exploratory. They are the default congestion control being used at Google. BBR for the TCP stacks, base stacks, and Swift for the OS bypass-based stacks, such as Pony Express, what I mentioned. Furthermore, we are also incubating some of the learnings that we've had from the OS bypass-based stacks and Swift as well into TCP, which is why in some of the IETF presentations, etc., you may hear of BBR.Swift, which is really cross-incubating some of the ideas from both.
I see. Okay, thank you. Appreciate it. Now, Konstantin, you talked about PNA, and obviously Google participates in PNA as far as I know. So tell me, how can PNA evolve to suit your requirements, especially for congestion control and transport protocols?
Yeah, it's a great question. I think overall, I think Google is really excited about PNA, right? I think they're a big fan of PSA on the switch side. And I think there's a huge potential for P4 on the NIC, and we really need, a portable architecture there. So I think overall, I'm really excited by this, and it's a great direction. I think if you look at these slides, right, I think for congestion control, there are certain things that you might not have currently in P&A, right? Like we need to accurately track the various states of these connections, for example. So I think these are things we should probably work together to get in there.
Okay. So related to that, I have a question that, in your work, you're using end-to-end delay as the congestion signal, and that's perfectly reasonable. And Google, as you said, has been using that successfully and all of that. But as you know, there are other mechanisms where people are using other indications, including based on switches, and trying to use those indications. So if for some of those schemes, how does this change as far as P4 expressibility is concerned, and whether P4 can be used for some of those kinds of operations that are not only based on end-to-end delay, but some indications coming from directly from switches as well?
So yeah, I can take on that question. That's such a great question, Guru. And going forward, I definitely see that actually the switches and the hosts will and should coordinate more in congestion control. Switches absolutely know the ground truth information, and hosts constantly keep probing in order to learn of the ground truth information, right? Which at some point, I think, they should absolutely coordinate more explicitly. And in that respect, P4, which is already has been, has made a lot more, is further along in the process in terms of congestion, expressing congestion control in the switches. And now with P4 in the NICs, I really hope that these two sort of directions that we are approaching from are going to meet, right? And we get one programmable plane for congestion control at both the NICs and the switches. So I think that we have a tremendous opportunity ahead of us in that matter. And the second, and maybe a more specific point, is that there are also opportunities in terms of if switches were to give out a lot of information on instantaneous values of queues or instantaneous utilizations, that's a lot of information for hosts. So I think that there is also an opportunity for us to figure out what is the right level of aggregation at the switches that should be done, and how often should the hosts actually receive this information or need to receive this information for a very responsive congestion control. And I know the community has had a large amount of work or some amount of work on this with respect to congestion control and switches, but I think we will see more of that actually taking shape in practice and landing in practice in future as well.
Konstantin, you want to add anything, or?
No, I think Nandita summarized it really well.
Okay, no, that's okay. I was just wanting to be sure. So I guess I know you didn't have time to talk about programmability and scheduler. So I want to give you at least a chance to say a little bit more. If you can elaborate on how scheduler as part of congestion control, how programmability can help, and how P4-based programmability can be helpful in that context.
Right. Yeah. Thanks for the question, Guru. I'm a huge fan of schedulers, and programmability in schedulers just seems like just the right thing to do. So let me actually set some context here, that why do we care so much about schedulers, right? Especially in the NICs with respect to transport. There are at least two aspects where schedulers really help transport and congestion control. One is what we've already spoken about under large-scale incast, traffic shapers and schedulers essentially time the packets, clock the packets out into the network, which is really helpful to handle aggressive traffic patterns like incasts. The second case is really what I was talking about earlier in the talk about bandwidth management schemes such as Bandwidth Enforcer, which shape not just a single 5-tuple flow, but they shape aggregates of flows. And shaping is therefore a very important construct that NICs offer. So I think that there is actually an opportunity out here that today we've thought a lot about traffic shapers in terms of pacing and traffic shaping, but we haven't really thought about data structures that can do both scheduling and traffic shaping, right? If I actually want to do rich scheduling, whether it's priority queue based or shortest remaining processing time, weighted fair queuing, as well as combine shaping with that, what does that data structure look like, right? And how can it be easily implemented in the path? So I think there's opportunity around that. There is also an opportunity to unify many schedulers in NICs. Schedulers are used not just for packets, but they're used for VMs or for higher level operations. And today, like, why is it that we can't have one scheduler that is programmable in a meaningful way that can handle operations, packets, or any other entities that we care about in NICs? A related point, or maybe a third point that I want to make is when it comes to scheduling, we often think about TX scheduling or in the transmit queues, right? But scheduling on the receive side of queues, on the receiver NICs, is actually just as important or probably even more important than the transmit side, because by the packet is, or the operation has already arrived at the receiver. So there is really nothing much you can do about it other than either drop it or schedule it or in some fashion. So I think there is actually a rich set of work to be done in this area going forward.
Okay, maybe my last question. So in your reference host stack, you did not take into account the virtualization or overlay networks. And as you know, most applications today in a lot of contexts work in the virtual and overlay networking context. So how does this change? Anything you mentioned about programmable congestion control and all of that, how does it change in the context of overlays and virtual networking?
That's actually another great question. I think that there is, probably another probably a 60-minute talk there on how to do overlay networking by itself, a virtualized overlay networking in NICs and making it programmable. But you hit upon a very interesting point that I think that actually at some point, well, this talk focused on transport and congestion control, but there is a point where overlay networking and transport and congestion control actually meet and need to work together and need to act in coherence to give end-to-end performance for VMs, right? And a concrete example of that is, say, scheduler and traffic shaper. For example, in overlay networking, it's quite common for entities like the bandwidth enforcer to enforce rates on aggregates of flows, while at the same time, congestion control is enforcing rate on a finer granularity flow, right, on a 5-tuple basis. But how do you actually reconcile these rates and enforce the right rate, which presumably is going to be the minimum of the rates along the path as well as along the different entities, and make the scheduler actually do the right, and program the scheduler to do the right thing. So I think that there is actually a lot of intersection points there. What I just mentioned is an example, and it would be great to probably have a future P4 talk, Guru, on that. Yeah.
Okay, sounds good. So is there any question I should have asked and didn't ask Nandita or Konstantin before we close out?
Well, I think maybe one summarizing thought, right? I think,
please.
P4 is traditionally, right, like the programming language, like for switch pipelines, right? I think it really makes sense to take it up a level, right? And think of other domains where we can apply it, right? And I think I've tried to lay it down a bit of a framework, right? Don't think too much about packets and stuff, right? There's many ways we can think about this. And yeah, I think congestion control is one, right? I think there are probably many other ways where we can apply P4.
Well said.
Very good. So again, I want to thank you both for a wonderful talk and a lot of good insights and stimulating talk. So again, appreciate your participation in P4 workshop. And, so with that, we will try to close it out.